Dear ladies and gentlemen, we have finally going to release the filtered orbits, and here I present you the first beta version of the system for the orbit analysis. So first of all, let me explain you what is orbits and what we are doing here. So the orbits are measured with two proximeters or other sensors in two directions. So this is the time domain signal measured for 1.8 seconds, or if I switch off filtration it will be for 2 seconds on the vertical and horizontal direction. So this is X and Y time domain signals. So here we have spectra from these signals, and you can see them in dBs or you can see them in microns. If you have a rotation speed sensor, you can also see them in orders, in rotation speed harmonics. You can change the spectral parameters, etc., etc. So the orbit plot is when we draw or make a chart from the X and Y axis. So X is here, Y is here, and if we put a cursor here and start moving it, you see that we have a movement across our orbit. So the shaft rotates like this. We can, once we have the TACO probe, we can see that the only one revolution. So here is the time domain signal from one mark of the TACO to another mark of the TACO. So this is just one revolution of the shaft. We can increase the number of these revolutions in here in the orbits. It is the second revolution, the third, the fourth, etc., etc. We can have very many different revolutions, and you see that the shaft is not stable. It goes mainly from left to the right, so in the X direction. You also see that in the time domain signal you have movement in vertical in the X much more than in the Y direction. We can also do the average. When we do average, we have this, for example, 10 revolutions, and each millisecond we take the mean value here. So in the columns, in each millisecond or even faster, we do the averaging. So for example, we put here just 1 and we start averaging. So this is the 2, the 3, 4, etc. So this is 10 averages or 11 averages, 10 averages. And we can, so these are the first 10 revolutions that are synchronously averaged. We can also put the second 10 revolutions that are averaged, the third, the fourth, and this we can do until the signal finishes. So here we can write something like 10 averages. So this is what was previously. What we have included additionally. First of all, I put here 1 and I put here 1. So first of all, if the rotation speed sensor we do not have it, or it produces the wrong signal, we can do the emulation. So we dispose the TACO probe marks and we enter a different rotation speed. So to enter rotation speed, there are 3 options. First of all, if you have a TACO, you can use it. If you don't have a TACO, you just can write it manually. For example, I can correct it to 50 and say OK, like this. Also, you can point the rotation speed on the spectrum. For example, I can say that here I have my rotation speed. I can adjust it according to the Henning window, use it, and say OK. So this is the emulation. If I have an orbit that doesn't have any TACO, for example, here I don't have any TACO, I can just use it from the spectrum. Again, adjust, use, OK. So this is the orbit that didn't have any TACO signal when it was measured. So the next thing that we have here is we have filtration. So we have several ways how to filter the signal. First, so we switch on filtration, and first of all we have low pass filter till the selected harmonic of the rotation speed. So here is the spectrum of our filter frequency response actually, and this is till the first harmonic of the rotation speed. So this is the first harmonic of the rotation speed, and everything else is filtered out. You can see that the decrease is more than 100 dB, so this is a very strong filter. So this is till the first harmonic, till the second harmonic, so we have 2 harmonic, till the third, fifth, and seventh. So this is till the 7th harmonic of the rotation speed. You can filter out your orbit. The second thing is the bandpass filter. The bandpass filter differs that it removes the low frequencies, the lower frequencies of your signal. So this is just the first harmonic, just the second, just the third, from first to the second, from second to third, and from the first to the third harmonic. This is a bandpass filter. Of course, you can average here everything that you want, and you can display many orbits here. So this is, for example, 6 orbits, each of them 8 averages. The next filter that we have is a narrow band filter. So this filter will remove also the frequencies in between of the harmonics. And if I select it, this is the first harmonic, and I can add the second, the third, the fourth, etc. So this is the fourth harmonics, and all the frequencies in between of these harmonics are removed by the filter. Again, you can see that we have about 100 dB attenuation, so this is quite a strong filter. The last one is the order analysis. The order analysis is used for the full spectra analysis. So here we have not an auto spectrum but the full spectrum. What is full spectrum? We have 2 signals in 2 different directions, and from them we combine a complex signal that has real and imaginary part. And we take a special FFT and we get a signal from the real part of our signal, the spectrum of the real part of our signal, and the spectrum of the imaginary part of our signal that we write it down in the negative. Actually, it is not exactly like this. There is more complex formula, but the idea is that we split our rotation of the shaft into direct and reverse direction. So the positive is in the direct direction, and in the negative frequencies is the rotation in the reverse direction. So the combination moves provides the actual rotation of the shaft. The full spectra were introduced by Bentley Nevada somewhere in the beginnings of the 90s. Bentley for the analysis of the defects of the journal bearings. So there are a lot of articles devoted to this, and you can read them and evaluate the situation. What they look at this spectra is the relationship between negative and positive harmonics of the rotation speed. So we have a cursor that moves symmetrically, and this is the first harmonic of the rotation speed. This is the second harmonic of the rotation speed, and what you are interested in the relationship. If the I switch off the dB, and if the positive is higher than the negative, it means that you have something like a disbalance. If it is opposite, for example, negative is higher than the positive, it means that this is something like a misalignment. There are a lot of things about it and a lot of symptoms, and we are going also to make an automatic condition diagnostics by these full spectra. Also, what we have is the harmonics spectra. So these are taken the positive and negative harmonics and just somehow printed or just drawn in one spectra, so that you can easily compare them. The orbit that we plot here is a model orbit that is built actually by something like inverse FFT on this harmonic spectra. So we take these harmonic spectra, we remove all the frequencies in between of the harmonics, and we just draw a model spectrum. That's why we do not average it, and somehow we just plot it. Here you also can use just one harmonic, the second harmonic, the two harmonics, the 3, 4, etc., etc. So you can add these harmonics or remove them. For example, if you remove the first harmonic, you will see something like this. The second, and we can, for example, see the odd harmonics only. It will be picture like this. So you can work with it. The other thing that we have here in this order analysis mode, we have the major axis. So major axis, if we just use the first harmonic, it will be the axis of this ellipse, the long axis. This is the major axis for the first harmonic, for the second, third, etc., for all harmonics. Also we have compression ratio. This is the relationship between the small axis of this ellipse and the large axis of this ellipse for all the harmonics. So this is for the second harmonic, etc. What else? What we have? We have the tilt of the major axis. So this is the angle of the major axis and the x-axis and how it develops in time. So for example, here we see that it with the 8 spectra, you can add maybe some more. The mean value is the blue, and these are the each revolution or each spectra that we can get from the spectrum. And the green ones is the deviation or root mean square error of these samples. So if you have some trend and your rotation will evolve, then you will see it here. So for example, if we make a standard filtration of just the first 3 harmonics, and we'll do it in 3 different ways. So for example, it will be order analysis, this will be narrowband filtration, this will be bandpass filter like this, and this will be low pass filter like this. You see that more or less all of them are equal. What else we can do? There is a very interesting filter. This filter is for the self-sustained vibration or the precession of the shaft. So this is below the half of the rotation speed. So I put one here, I put one here, and I use the filter that is below the rotation speed. So this is half of the rotation speed. So we can see that during one revolution our shaft made a precession like this. We can add the number of revolutions and see that it has a precession like this. During, say, 18 revolutions, it moves like this, and you can say that the amplitude of this movement here is about 2 microns, and if we switch off the filtration, we see that our diameter of the orbit is 6. So actually 2 of these 6 is the precession, and you can also see it on the vertical or on horizontal and vertical, that they are a little bit different. So this is the precession of your shaft. We can also judge on it. So this is what we have done to the orbits. If we use an orbit that we measured last year on the gas turbine, it was measured on 3 supports, and we can see it filtered with up to 3 harmonics of the rotation speed. So this is one support, and we can use different types of filters like this. We can also do some order analysis of it. We can take the second support here. We can take the third support here, and we can compare what is going on. So thank you very much for your attention. This is a beta version, and your comments and views are highly appreciated. In the next video I will show you some of the other examples of the orbits that can be quite interesting. Thank you for your attention.